Okay, now that we have solved part A, let's move on to part B. Calculate the value for the specific rate constant, baby K, at 30 degrees Celsius and specify the units. So K is a rate constant, but it's only constant when temperature is held constant. So they're saying specifically at 30 degrees Celsius because this reaction was carried out at 30 degrees Celsius. And units, very important for K, and I'll show you how to get those in just a moment. So it doesn't matter which experiment that you choose to use to do your calculation. I'm just going to choose experiment number 1. Okay? You could choose 2, 3, 4, 5, whatever. It doesn't matter because K is a constant. We're talking about the same reaction at the same temperature, so no matter which one that you choose, you should get the same answer for K. So I know that this is our rate law, or also known as our rate expression. I'm going to plug in everything that I know for experiment number 1, okay, into our rate expression. So the rate for experiment number 1 is 8 molarity per hour. So 8 molarity per hour. So 8 molar per hour. That's equal to K times the concentration of A for experiment number 1, which is 0.24 molar squared, times B, 0.48 molar to the first. Okay. First thing I want you to do is just do the algebra. We'll worry about the units later. So square 0.24, multiply by 0.48, and solve for K. K equals 289.35. And so let's check sig figs real quickly. Go back to your data table and see how many sig figs. Each number has 3, so I'm going to round this to 3 sig figs. So K, baby K, equals 289. Okay, there's my numerical answer, but I have to include units with K. So if I was to look at this 0.24 molar, notice that it says squared. So on this side of the equation, I have K, and let's just focus in on what the units would be. Molarity squared. And then I have molarity to the first, so it's molarity to the first power. And on the left-hand side, I still have capital M, molarity over hours. And so let's clean this up a bit. So molarity over hours is equal to K times molarity cubed. So divide both sides by molarity cubed. And you'll isolate K. So really this part here, we are going to rewrite this as multiplication for fractions. So that's molarity over hours times 1 over molarity cubed. And so when I multiply these together, I have a molarity in the numerator, and then I end up with 3 molarities, or molarity cubed, in the denominator. So it becomes molarity cubed times hours. Okay. That molarity on the top is going to cancel and becomes a 1. And the number of molarities, or molars, on the bottom becomes 2. So we're left with 1 over molar squared times hours. And that is the unit of our rate constant. So K is equal to 289, 1 over molarity squared times hours. And that would be your final answer. You could rewrite that using negative exponents. You could also say K is equal to 289 molarity to the negative 2 times hours to the negative 1. That is also acceptable. Okay. I'm going to tell you a little shortcut. Okay, because you don't have time to do all of this math over here and figure out the unit of K. The shortcut for units. Okay. First of all, determine your overall order. Our overall order is 2 plus 1. 2 plus 1 is 3. Okay, so the unit on K will always be 1 over molarity raised to some power, and it's going to be the overall order minus 1 every single time, and then times your unit of time. Okay, this case it's hours, sometimes it's seconds, sometimes it's minutes, sometimes it's days, whatever the unit for time happens to be. So your unit for K will always be 1 divided by a capital M for molarity, and the exponent on molarity is always the overall order minus 1. So for our example, our overall order was 3. And if you look and see what we ended up with our exponent on our molarity for our unit of K, it was a 2. Okay. So it is 3 minus 1. I got that 2 on that molarity, and then boom, tack on the hours, and you're done. So this shortcut, very helpful for kinetics problems, because we love to ask you for the unit of K.